Now I want to move on to the second topic here, which is desalination. So in the video, the professor mentioned how in most times pasteurization is done by boiling the water, which is essentially distilling it, which is not required. But for desalination, we require it in most cases, and we'll talk about this. To me, this is a very interesting technology, and it's a technology that is probably going to be very important for all of us living here in the Southwest, right? So we need to start thinking about this more seriously, in my opinion. One very interesting thing, which is, you guys saw this before, is this plot. So this is an interesting graph, which essentially shows the water stress indicator, so where the populations are stressed for water. And this overlaps almost in a highly correlated fashion with the amount of sunlight you receive. Right? You don't have problems of water up in the Scandinavian countries, but you do have in the lower latitudes, right? So, but can we take advantage of this resource of sunlight in order to do that? That's basically the motivation. Oops. So we all know that this happens naturally, so this is how we all drink. So just to remind ourselves, what does this mean? The water from the ocean or the lake or whatever gets evaporated, become clouds, it moves over, cools down, hits a mountain, whatever, it comes down with rain, and it can go back into the lakes and into the aquifers and whatnot. But this can be can have a high salt content. But of course, this distillation means that you're leaving the salt behind, you're getting pure water up, right? Because of water vapor. That is the process of separating everything else from the water and potentially the purest way to get desalination done. I would call it natural solar desalination, right? Now, how is this done? So desalination plants exist today. So I think maybe more than 3/4 of the water in Saudi Arabia, for instance, is desalinated. I think more than 90% in Israel is desalinated. In Mexico has, I think, the 3rd largest water desalination plant in the world. There is one in Southern California, which is like 5th or 6th largest, so near San Diego. So if you're ever there, it's an interesting place. But how does it work, right? There are different ways to do this. The simplest way to think about desalination is with osmosis. Now, what is osmosis? So to understand osmosis, we can just look at the left-hand side. So imagine I have a very salty solution, seawater, whatever, on one side, and on the other side, I have pure water, okay? No salt. And they're separated by a filter. Now, this filter is special. This filter will allow water molecules to pass through because they're tiny, but salt molecules are not allowed to pass through because they're big. Salt is sodium and chlorine, and they form the crystal lattice because of the Coulombic forces, right? So you probably all heard about it. They're much bigger than the molecular formulation of salt is much larger than water, so you can easily separate them with the filter. Now, what will happen if I do nothing? I just let it sit. I have the answer here, right? What will happen?
Well, I assume the pressure will stop.
What will happen if I just leave it starting this way? You're right, but let's see what will happen in this situation. Not yet. It'll go, because remember, this is basically a sorting machine. So I should point here. Filter is a sorting machine. The more water molecules will flow this way, no salt molecules will go this way. So all the water will start slowly moving this way. And this is called osmotic pressure. So they will not equalize. It's very interesting. It's exactly the same thing that happens if I take a bottle of perfume and open it at one corner of the room. Even back there won't smell it until a few minutes later, it'll go out. And this is because of the second law of thermodynamics. The second law of thermodynamics says entropy will always increase, right? So that means this is highly ordered. This is highly ordered, mostly salt, fixed concentration. It's mostly water. That order gets lost. It becomes more randomized, okay? And you can use this to do work, this flow and things like that. They call it osmotic pressure. But we want to do the opposite. That's what we want, right? We want the water to go the opposite way. That means you have to go against the second law of thermodynamics. The second law of thermodynamics dictates that you cannot get pure water from salt water without doing work. It cannot come from free. It's the exact same situation that happens if I drop a teacup and it breaks into many pieces. That is allowed by second law of thermodynamics, but the opposite is not. Physics doesn't disallow it other than the second law of thermodynamics. Think about it again. If I break a teacup into lots of pieces, there's nothing preventing in physics from it coming all back together and becoming a teacup other than the second law of thermodynamics. The exact same situation here. Order to disorder. Okay, this dictates everything, by the way. The arrow of time, our aging, expanding universe, all this stuff. Exact same thing. So what does that mean for the purposes of us? For us is that we have to do work to get pure water. And the work we have to do is to put pressure on the brine to push it through the filter. Now, if I start pushing here, what will happen? The water can flow this direction, but the salt can't. Right? So eventually, this level will go up, this level will go down, and that's okay because I'm doing work, and I will get pure water. And this is simply what happens in a desalination plant in a much more complicated way. A reverse osmosis plant, sorry, I should. Reverse osmosis desalination plant. Okay? Unfortunately, so first of all, I should say, in an actual plant, it's not as simple as this because you have to do this in stages. So you have a kind of a low quality filter, which removes, let's say, 50% of the salt, and you push it through. And then you send it through another phase where you have a higher quality filter, which removes, let's say, 75% of the salt, and so on and so forth. So it's really like this progression in massive, huge tanks, right? Unfortunately, this requires a lot of work. Requires huge amounts of energy. This is why if you go to places that use water desalination, your water bill is really, really high. Okay, it's very, very expensive to do. So that is your problem, right? That's a problem that you guys can solve. Think about solving. Because today this is done by using fossil fuels, right? You just run a whatever motor, compressor, is it through gas, whatever it is. Can anyone see any other problems with it? Energy and cost is an obvious one. Anything else? So this simple principle, nothing complicated.
Well, I assume over time you're going to plug the filter.
Exactly. So over time, salt will build up here, right? What does that mean? It will get harder and harder to push the water through, which means that as you get more and more water, it becomes exponentially harder. So if you actually do an integral of the amount of energy you have to put in it, it actually blows up. And the only solution is you have to replace the filter. So fortunately, there are many companies like 3M has a huge business essentially making these kinds of filters. There are meters, billions of meters of filters are made. It's a massive industry, massive material science problem. There's huge amounts of innovation happening. Some of you are probably from material science, probably thinking about these kinds of problems. So that's an example. Okay, now how could you do this with light? Well, I mean, what are the possibilities of solving that problem, those problems with light? Maybe not the filter problem yet. One is to use photovoltaics as a primary energy source. And I'll just show you a simple example. So this is an example from MIT where essentially it's a simple system. They have a water storage tank. They have the desalination system. So they have basically solar panels. And they have some control electronics. I'll come back to that. They have a tracking system. And then they simply use the photovoltaic panels to run a desalination pump. So push the water through the filters. Simple? Okay, I'm going to ask you something about this later. So let's pay attention. So this is on the roof of one of the buildings. I was a student there, so I know about this. So you can see it's tracking the sun, it's pumping the water into the aquarium, building it up. So you can see the video. They put a nice rubber ducky so you can see it. And this is important. Over here at the bottom, you're seeing the solar radiation, watts per meter squared. We'll come back to that as a function of time. So during the day, you get this, sun's pretty high, yeah, it's 5 a.m., 10 a.m., whatever. Okay, 3 o'clock. Yeah, okay. Does anyone see any problems with this? Actually, take 30 seconds and think about this for a second. Tell me, do you see a problem? Don't shout out. I want you to discuss first. You don't have to wait. You can discuss now. Any problems with this? You don't have to shout out. Take 30 seconds. We'll be quick. And for those of you on Zoom, I will look at the chat. Let's see. And by the way, great comments before, so let me see. Changing filters, but that's a common problem to everything. Pressure, okay. Anything? Degradation of the panel? Yeah, yeah, happens, yeah. You should remind me your name, I can't remember. Emmett, yes. Yes, yes, we'll get into this, yeah. So, I heard something. The pump is an engine, right? Just like your car, right? When your car runs, what is the most efficient way to run your car? Is it on a highway, or is it in a smaller road where you're stopping for every stoplight? Which one's more energy efficient? Why?
It's already moving, right? It's already moving and moving quickly, right? So
it's a constant velocity.
Yeah.
So the constant, say that again? Yes, exactly. So the constant velocity of the engine allows you to run things at the optimal efficiency. It's the exact same thing here for a pump. Okay, so if you have a filter on your swimming pool or something, you want to run it at a constant speed. You don't like. So what is the problem here? Exactly. This is not constant. There's nothing but constant, right? There's nothing constant about this, right? You're getting some jumps, all these delta functions, all nonsense, right? This is not good, very bad. So you have to handle this, and that was the whole purpose of this particular project. They handled this, and I don't have the details yet, but they handled this in the control electronics, in this stuff here. Basically, you have a battery, ensure you charge it, make sure what you send it is constant. Many of you are electrical engineers, you know about this better than me. Okay? So that's an example of a problem that they solved, right? Very interesting. Maybe there are ways to do this optically as well, maybe, potentially. But why is, just a quick comment, why is this important? If you can make it portable, you could use it for disaster relief. We had the floods in Hawaii recently. Water is not easily available, even in Hawaii. So, you got to deal with that, because when floods happen, obviously they're contaminated. So it's essentially an optimal controls problem, challenging problem, actually, mathematically. So if there are some ideas of optical engineering that can help, that could be quite interesting. Okay, so something to think about. We won't go into that yet. Let me see what else I have here. So there are much simpler solutions. In fact, I saw a very interesting, actually I will show you at the end of the class. So I got an email the other day about exactly doing this in the Great Salt Lake. People want to do this. Now, what is this? Let's see what this is. So in a terminal lake like this, you have a high salt content, but the point is that the salt being heavy will go to the bottom. So you get the high salt content brine at the very bottom here, and then you have some sort of gradient, and then you have a low salt content, and that's cooler, because the brine actually has higher absorption of the light, so it will get hotter first. So what happens is that you get a temperature gradient. So this side is hot, this side is cold, and that's what is used to run a heat engine, and we'll see this again and again. So, but in this case, it's fairly simple. You basically run some sort of, I mean, this example, they're running a brine through some sort of tubing here, usually copper or whatever, and then you have some sort of organic working liquid that gets heated up. In the old days, it used to be freon and chlorofluorocarbons. Now it is different stuff. But it becomes liquid. It turns from liquid to gas. Then it goes through and runs a turbine and creates electricity. And then it goes up here, cools on the condenser because that's a cold part of so this is the cold water here. And then it flows down and goes through this pump into the evaporator. And then it runs a cycle. Okay, so it's a fairly simple idea, old idea. If we can do this in Salt Lake, you could create power, right? It's kind of nice. Unfortunately, the efficiency is low. So the problem is it's about 10, 15% typically. The nice thing is that there's no tracking required. It works for all light, right? Whether it's cloudy, whether it's bright and sunny. Sometimes people use it for heating as well. So you can imagine similar sort of stuff. Of course, there are more fancier ways to do this. You can put it at the focus of a parabolic collector and distill in the water. Yeah, sorry.
Yeah, curious about that. So my personal experience,
yeah,
when I swim in the ocean, it
yeah,
gets colder as I go down.
Yeah. Okay, that is very different because it's much deeper. Okay. So the sunlight doesn't it gets absorbed fast. Yeah. So the solar stills are typically very shallow. So you're right. It can work when it's super deep in the Salt Lake. Yeah. Well, there are regions that are shallow, right? I'm not an expert in this. Yeah, I just saw an email from a foundation where they're asking for ideas to actually do something like this. In fact, I just got it like 2 days ago or something, so I didn't read it carefully. Yeah, so you can do distillation by just putting it in the focus of a solar concentrator, just like in a cooker, and that's a nice use. Of course, you have to deal with corrosion. So one thing we didn't talk about is that salt is highly corrosive. So if you pass it through the pipes, obviously you have to deal with that. Something to keep in mind, can be expensive. You can also have very simple things like a single effect solar still. Now this, nothing super complicated. I'm gonna go through it a little fast, but essentially you have something like a greenhouse and there's a dirty water inlet here. It simply heats up because of the sun, but the vapor gets trapped at the top on the ceiling and essentially condenses, right? Because the ceiling is a little cooler than the water itself, and then it gets collected here and the fresh water is removed. So let's do a quick back of the envelope calculation, and I'll explain to you why. So we have to do this quickly because we don't have a lot of time. The energy, and all of you on Zoom should do this too. You can take a piece of paper if you want. Energy to evaporate 1 kilogram of water at 30 degrees C is about 2.4 million joules, okay? If the solar insolation is 250 watts per meter squared, how much water can be produced per unit area per unit time? Let's ignore the efficiency for now, assume it's 100% efficient. Take about 30, 60 seconds. You can talk if you want, and then we'll go through it. And the reason I want you to do this is because I want you to think in back of the envelope numbers. Okay, I'll let you do it first, and then we'll talk. You can talk if you want. What did I say? I don't remember, actually. Okay, watts are joules per second. Everybody knows that, so I just converted that. What am I asking here? How much water is produced per unit area per unit time? So this is joules per kilogram. Correct? Everyone okay with that? Okay. And question I'm asking is how many kilograms? My answer should be in kilograms. Like, can I produce for 1 meter squared per second, right? This is what I'm asking, correct? Everybody see that? How much water per unit area per unit time? So how do we get that? Just purely from units, forget the physics for the time being. I can take this. This is, no, I shouldn't be doing it. Does anyone want to say?
Yeah, you just do the dimensional analysis.
Yes, exactly. I can just take this and divide it by that, right? What do I get? Joules cancels out. Kilogram goes on the top. A second per meter square goes at the bottom. That's exactly that. And of course, that makes sense. It's common sense, right? If I have 250 joules per second per meter squared, it takes that many joules for a kilogram. I take that. This is the rate in time and area. That is the rate in mass. If I divide it, I'll get the mass. Okay, so I went through it a little fast, but the point I'm trying to make is not this particular problem, but be able to think in dimensional analysis, because this class, I don't really care if you get the exact number, but you need to be able to understand what to do. Okay, so if you show steps, it's very important to show the steps, even if the answer is wrong, which is true in most classes, but here it's especially important to just have intuition of what it is that we are doing. Okay. So what's the answer? Anybody get it? Anyone?
I got 104.2 times 10 to the negative 6 kilograms per second per meter squared.
Great, thank you. So I'll say one more thing here. I'm going to make a lot of approximations. So I'm going to make this 2.4 into 250. And I'll get that, okay? Back of the envelope. And then what's my answer? 10 to the minus 4 kilograms, which is 0.1 grams per meter squared per second. Okay, sorry, it's down there. Do you see that? At the end of the day, I don't really care what the exact numbers are, but I care that I'm getting less than a teaspoon of water for 1 meter squared, right? 0.1 grams, maybe a teaspoon, I can't remember exactly. Okay, that's what I want you to get the intuition for, like the scale of things, right? So that means for this to be useful, I need some massive setup, right? Unless I do something else. So again, another problem, right? That's the way you should see it, an opportunity. Typical efficiencies are not great. They're like 30, 40%. So, you have to be, this number is assuming 100% efficiency. So you're going to have to divide it by a third or even more. So not great. So there's a lot of things still to be worked out. Okay, anyway, my whole point was don't worry about exact answers. Think in back of the envelopes, orders of magnitude, dimensions. Get a feeling for it, intuition. Okay, this is very important in this class. Don't worry about doing all the math super carefully. I mean, you should do it if you can, but much more important to gain that understanding. I won't go through this in the interest of time, but this is basically the same thing, except that now you have a greenhouse, you have plants in it, and this is actually used in many arid regions, especially, for instance, in North Africa and Middle East and so on. Maybe you might be familiar with in some cases, yeah. I'm not very familiar with them, but I know they're used in lots of places. And of course, corrosion is a challenge. So I'm going to skip that. So if we were to summarize what we talked about in desalination, we really have two approaches. One is a direct approach. We use sunlight to create the distillate. We can have stills and all that stuff. Or you can have an indirect approach where you convert the sunlight to electricity and then use electricity to create water. It's pretty straightforward. You can also think about thermal approaches as well. We didn't talk about it. It's an option as well. But let's keep going.